Welcome to today's session. In this video, we'll tackle problem number 1921, eliminate maximum number of monsters. Together, we'll explore an interesting problem-solving journey, breaking it down step by step. Let's dive in and see how we can maximize the number of monsters eliminated. Ready? Let's get started. In this problem, you're tasked with eliminating monsters in a video game before they reach a critical point, position 0 on the x-axis. Each monster starts at a given distance from position 0 and moves toward it at a constant speed. You have a weapon that can eliminate one monster per minute, and your objective is to eliminate the maximum number of monsters before any of them reach position 0. You're provided with two integer arrays, dist and speed. The dist array represents the initial distances of the monsters from position 0, and the speed array indicates the speed of each monster in units per minute. The task is to calculate and return the maximum number of monsters you can successfully eliminate before any of them reach position 0. Now, let's consider the first example. The input arrays are dist equals 1, 3, 4, and speed equals 1, 1, 1. Here, monster 0 is at a distance of 1 and moves at speed 1, so it will reach position 0 in exactly 1 minute. Similarly, monster 1 is at a distance of 3 and moves at speed 1, reaching position 0 in 3 minutes. Monster 2 starts at distance 4, moving at the same speed, and will reach position 0 in 4 minutes. To maximize the number of eliminations, you can eliminate monster 0 in the first minute, preventing it from reaching position 0. After eliminating monster 0, you have time to eliminate monster 1 at minute 1 since it still has 2 minutes before reaching position 0. Finally, monster 2 can be eliminated at minute 2, as it won't reach position 0 until the 4th minute. By eliminating all 3 monsters in this order, you successfully prevent any of them from reaching position 0, and the output is 3. This example demonstrates how the elimination order is critical to achieving the maximum result. Now let's examine another example with the input arrays dist equals 1, 1, 2, 3, and speed equals 1, 1, 1, 1. Here, monster 0 and monster 1 are both at distance 1, and they move at the same speed of 1, meaning they will both reach position 0 in 1 minute. Monster 2, starting at distance 2, will take 2 minutes, and monster 3, starting at distance 3, will take 3 minutes. In this scenario, you can eliminate monster 0 at minute 0. However, during this time, monster 1 will reach position 0, making it impossible to eliminate more than one monster. Therefore, the output is 1 in this case. In the third example, the input arrays are dist equals 3, 2, 4, and speed equals 5, 3, 2. Calculating the time each monster takes to reach position 0, we find that monster 0 will reach in 0.6 minutes, monster 1 will reach in approximately 0.67 minutes, and monster 2 will reach in 2 minutes. Because the first 2 monsters reach position 0 so quickly, you can only eliminate one monster, regardless of the order. Thus, the output is 1. This example highlights the impact of high speeds and short times to reach on the number of eliminations you can achieve. To solve this problem efficiently, the first step is to compute the time each monster takes to reach position 0 using the formula time, I equals dist, I/speed, I. Once you have the time to reach values, sort the monsters by these times in ascending order. Then, employ a greedy approach where you eliminate monsters in order of their time to reach, ensuring that the current time does not exceed the time to reach of the next monster. This strategy allows you to maximize the number of eliminations. Finally, return the total count of monsters you successfully eliminate before any of them reach position 0. To approach this problem, we first consider a brute force solution. The intuition behind this method is straightforward: eliminate monsters one at a time based on the order in which they reach position 0. To do this, we calculate the time each monster takes to reach position 0 using the formula time, I equals dist, I/speed, I. Once we have these times, we sort the monsters in ascending order of their arrival times. Then, we iterate through the sorted list, eliminating one monster at a time and updating the current time. If a monster reaches position 0 before we can eliminate it, we stop the process. While this approach is simple and intuitive, it has some limitations. The main drawback is that it doesn't add any optimization beyond the basic logic. With a time complexity of O, n log n, for sorting and an additional O(n) for iteration. It's not the fastest approach possible, but it's a good starting point for understanding the problem. Now, let's consider an optimized approach using a minute heap. The key observation here is that sorting the monsters by their arrival times is crucial to solving the problem efficiently. A heap or priority queue could theoretically allow us to maintain this order dynamically. However, this added flexibility is unnecessary because sorting the arrival times once beforehand achieves the same result with less complexity. The overhead of repeated heap operations, such as insertion and extraction, makes this method less efficient in practice. Therefore, we opt for a simpler strategy that still leverages the idea of sorting but avoids the additional computational cost of a heap. The chosen solution, which involves pre-computing and sorting the arrival times, is both cleaner and faster. By focusing on when each monster reaches position 0, we can handle them in the optimal sequence with minimal overhead. The breakthrough in solving this problem lies in a few key observations. First, the only relevant factors are the monsters' arrival times, determined by their distances and speeds. Once we compute these arrival times, the problem transforms into a straightforward scheduling task. Sorting the times ensures that we process the monsters in the exact order they need to be eliminated, maximizing the number we can handle before time runs out. Comparing the different approaches, we see clear trade-offs. The brute force method is conceptually simple but involves repetitive computations, making it less efficient. The heap-based approach adds dynamic ordering but introduces unnecessary complexity when a static sort is enough. In contrast, the sorting-based solution combines clarity with efficiency, making it the best choice. Its simplicity aligns with the problem's structure, ensuring we achieve the optimal result with minimal computational effort. To solve this problem, we need to eliminate as many monsters as possible before any one of them reaches position 0. Each monster has a position and a speed, which determines how long it will take to get to 0. This time is calculated using the formula time equals position/speed. The first step in our algorithm is to compute this time for each monster and store the results in a list. These times represent when each monster becomes a threat that we need to address. The next step is to sort these times in ascending order. By sorting, we ensure that we prioritize the monsters that are closest to reaching 0, as they pose the most immediate danger. This sets up the foundation for our elimination strategy, ensuring that we address threats in the correct order of urgency. Once we have the monsters sorted by their times, we simulate the elimination process. We start by initializing two variables, counter, to keep track of the number of monsters we've eliminated, and current_time, representing the elapsed time as we process each monster. We then iterate through the sorted list of times. For each monster, if the current_time is less than the monster's time, it means there's still an opportunity to eliminate it. We increment both the counter and the current_time, simulating the act of eliminating the monster. However, if the current_time is equal to or greater than the monster's time, it means the monster has already reached position 0, making further eliminations impossible. At that point, we stop the simulation. By the end, the value of counter gives us the maximum number of monsters that could be eliminated before any reaches 0. The key to the algorithm lies in its efficient approach. Sorting the monsters by their time to reach position 0 is a greedy strategy, ensuring that we always address the most urgent threats first. This minimizes the chances of monsters reaching 0 prematurely. The simulation process itself mirrors real-time decision-making, where we eliminate monsters as long as we have enough time to do so. By stopping early when a monster cannot be eliminated in time, we avoid unnecessary computations, making the algorithm both effective and efficient. In terms of data structures, the array used to store the calculated times allows for quick sorting and iteration. The counter variable tracks how many monsters have been eliminated, while the time variable helps manage the simulation. The time complexity of the algorithm is dominated by the sorting step, which is O(n)(log(n), while the other operations, like calculating times and simulating eliminations, are O(n). The overall space complexity is O(n), as we only need to store the list of times. Finally, it's important to consider edge cases. If there are no monsters, the algorithm simply returns 0 since there's nothing to eliminate. If all monsters reach position 0 at the same time, the algorithm will eliminate as many as possible until the elapsed current_time exceeds their time. For monsters with a speed of 0, the time to reach 0 is effectively infinite, meaning they can always be eliminated unless the problem constraints indicate otherwise. If negative positions or speeds are encountered, these are generally considered invalid inputs unless the problem explicitly allows them. Handling these edge cases ensures that the algorithm remains robust and performs as expected across a variety of scenarios. This solution calculates the maximum number of monsters that can be eliminated before any of them reach position 0. The process starts by calculating the time it takes for each monster to reach position 0 using the formula time equals distance/speed. These times are stored in a list, and the list is sorted in ascending order to prioritize the monsters that will arrive the soonest. The algorithm then iterates through the sorted list of arrival times. It uses a counter current_time to track the current time at which we can eliminate monsters. For each monster, if the monster's time to arrival is greater than the current time, it means we can eliminate that monster. The eliminated counter is increment, and current_time is also increment to reflect the next time unit. If at any point a monster's arrival time is less than or equal to current_time, it means that monster reaches position 0 before it could be eliminated, and the loop breaks. The number of monsters eliminated so far is returned as the result. This approach ensures the maximum number of monsters are eliminated by always handling the most urgent monsters first. The sorting step has a complexity of O(n) log n, and the subsequent iteration through the list is O(n), resulting in an overall time complexity of O(n) log n. Here, we start by defining our solution class and the method eliminateMaximum, which takes two arrays, dist and speed. The dist array represents the distance each monster is from position 0, and the speed array represents how fast each monster is moving. Our goal is to calculate how many monsters we can eliminate before any of them reach position 0. First, we calculate the time each monster takes to reach position 0 by dividing its distance by its speed. This gives us the time to reach array, where each element represents the time it takes for a specific monster to arrive. Once we have this calculated for all monsters, we sort the time to reach array in ascending order. Sorting is important because it ensures we handle the monsters in the order they become a threat. After sorting, we initialize two variables, eliminated, to track how many monsters we've successfully dealt with, and current time, to represent the time we're simulating. Now, we iterate through the sorted times and start checking each monster's arrival time. If the current time is less than the monster's arrival time, it means we have enough time to eliminate the monster. In that case, we increment the eliminated count and also increment the current time to simulate that 1 unit of time has passed. However, if the current time is equal to or greater than the monster's arrival time, it means the monster has reached position 0 before we could eliminate it, so we break out of the loop. Finally, we return the eliminated count, which represents the maximum number of monsters we could eliminate before any of them reached position 0. By using this approach, we ensure that we handle the monsters in the most efficient order and maximize the eliminations while adhering to the constraints of the problem. To solve the problem eliminate maximum number of monsters, we need to calculate how many monsters can be eliminated before any of them reach position 0. Each monster is initially at a distance defined by the array dist, and it moves toward position 0 at a constant speed defined by the array speed. Our approach begins by calculating the time it takes for each monster to reach position 0 using the formula time_to_reach, I, equals dist, I/speed, I. For example, if dist equals 1, 3, 4, and speed equals 1, 1, 1, the times are calculated as follows: monster 1 takes 1/1 equals 1.0 seconds, monster 2 takes 3/1 equals 3.0 seconds, and monster 3 takes 4/1 equals 4.0 seconds. This gives us the array time_to_reach equals 1.0, 3.0, 4.0. Next, we sort these times in ascending order to prioritize eliminating the monsters that will arrive first. After sorting, we have 1.0, 3.0, 4.0, which will guide the order in which we attempt to eliminate them. With the sorted time_to_reach array, we now eliminate monsters one by one, keeping track of the current time spent eliminating them. Starting with current_time equals 0, we iterate through the array. For monster 1, time underscore to underscore reach 0 equals 1.0 and current underscore time equals 0. Since the current time is less than the time it takes for this monster to reach position 0, we successfully eliminated, increment eliminated to 1, and update current underscore time to 1. For monster 2, time underscore to underscore reach 1 equals 3.0 and current underscore time equals 1. Again, the current time is less than the arrival time, so we eliminate this monster, increment eliminated to 2, and update current underscore time to 2. For monster 3, time underscore to underscore reach 2 equals 4.0 and current underscore time equals 2. The current time still allows us to eliminate this monster, so we increment eliminated to 3 and update current underscore time to 3. At the end of this process, all 3 monsters have been eliminated, and the result is eliminated equals 3. For a different example, consider dist equals 1, 1, 2, 3, and speed equals 1, 1, 1, 1. First, we calculate the times for each monster. Monster 1 takes 1.0 seconds, Monster 2 also takes 1.0 seconds, Monster 3 takes 2.0 seconds, and Monster 4 takes 3.0 seconds. This gives us time underscore to underscore reach equals 1.0, 1.0, 2.0, 3.0. After sorting, the array remains 1.0, 1.0, 2.0, 3.0. Moving on to elimination, we start with current underscore time equals 0. For monster 1, time underscore to underscore reach 0 equals 1.0 and the current time is less than its arrival time, so we eliminate it, increment eliminated to 1, and update current underscore time to 1. For monster 2, time underscore to underscore reach 1 equals 1.0 and current underscore time equals 1. This time, the current time is equal to the arrival time, meaning we cannot eliminate this monster. At this point, we stop the process, and the final result is eliminated equals 1. In another example, with dist equals 4, 2, 3, and speed equals 2, 1, 1, we calculate the time it takes for each monster to reach position 0. Monster 1 takes 4/2 equals 2.0 seconds, Monster 2 takes 2/1 equals 2.0 seconds, and Monster 3 takes 3/1 equals 3.0 seconds. This gives time underscore to underscore reach equals 2.0, 2.0, 3.0. Sorting the times results in 2.0, 2.0, 3.0. Now, we eliminate monsters while tracking current underscore time. Starting at current underscore time equals 0, monster 1 has time underscore to underscore reach 0 equals 2.0, which is greater than the current time, so we eliminate it, increment eliminated to 1, and update current underscore time to 1. For monster 2, time underscore to underscore reach 1 equals 2.0 and current underscore time equals 1. Since the current time is still less than the arrival time, we eliminate this monster as well, increment eliminated to 2, and update current underscore time to 2. Finally, for monster 3, time underscore to underscore reach 2 equals 3.0 and current underscore time equals 2. Again, the current time allows us to eliminate this monster, so we increment eliminated to 3 and update current underscore time to 3. All 3 monsters are eliminated, making the final result eliminated equals 3. To analyze the time complexity of our solution, let's break the process into its individual steps. First, we calculate the time it takes for each monster to reach position 0. This involves dividing the distance of each monster by its speed. Since we're iterating through the input lists once, and there are n monsters, this operation takes n time. Next, we sort the list of calculated times in ascending order. Sorting a list of size n using an efficient algorithm like timsort, which Python employs, has a time complexity of n log n. Finally, we iterate through this sorted list to determine how many monsters can be eliminated before the next one reaches position 0. This iteration requires a single pass through the list, contributing another n to the time complexity. By summing these up, we can start to see the overall time complexity of the solution. Now, when we combine the contributions from each step, the total time complexity becomes n for time calculation plus n log n for sorting and another n for the iteration. This simplifies to n log n, which is the dominant term due to the sorting step. Moving to the space complexity, the solution uses some additional space for the time underscore to underscore reach list, which stores the calculated times for all monsters. Since this list grows proportionally with the number of monsters, it requires n space. Python's sorting algorithm, timsort, is designed to sort in place, which means it typically needs 1 extra space. However, in some cases, temporary storage may be required during the merge phase, potentially using up to n space in the worst case. Additionally, the algorithm uses a few auxiliary variables like eliminated and current_time, which take constant space, or 1. The total space complexity is therefore dominated by the time_to_reach list, resulting in n. To put this in perspective, let's compare the optimized approach to a brute force method. A naive solution would simulate the elimination of monsters step by step, checking each monster's position at every time increment. This would involve iterating over all monsters repeatedly, leading to a time complexity of n squared. The space complexity, however, would still remain n for storing the positions of the monsters. By contrast, the current solution uses a greedy strategy along with sorting, reducing the time complexity to n log n, while maintaining the same space complexity of n. This optimization is particularly impactful for large inputs, where the growth of an n squared algorithm would be prohibitively expensive compared to n log n. Finally, let's consider how the algorithm performs in different scenarios. In the best case, where all monsters arrive at position 0 at the same time, the algorithm still has to compute the arrival times and sort the list. As a result, the time complexity remains n log n. For an average case, where monster speeds and distances vary randomly, the algorithm performs the same set of operations, time calculation, sorting, and iteration, yielding an average case time complexity of n log n. Similarly, in the worst case, where monsters have arrival times that are extremely close together, the algorithm still requires sorting and iterating through the list, so the time complexity remains n log n. In all cases, the space complexity is n, as it mainly depends on the size of the time_to_reach list, which scales with the number of monsters. When working on this problem, there are a few common mistakes to watch out for. One frequent error is processing monsters in the order they are given, instead of sorting them by the time it takes for each monster to reach position 0. This misstep can lead to incorrect results because faster monsters, which pose an immediate threat, must be dealt with first. To address this, you should calculate the time for each monster using the formula time equals position/speed and sort them based on this value. Another common mistake is using integer division while calculating time, especially in languages like Python or Java. This can cause inaccurate results for non-integer values, so it's important to ensure you use floating point division. Additionally, edge cases often get overlooked. For example, consider scenarios where all monsters start at position 0 and require no movement, monsters with 0 speed that remain stationary, or very large inputs where an optimized approach is critical. Lastly, avoid brute force solutions for large inputs, as simulating every elimination can be computationally expensive and lead to time limit exceeded errors. Instead, focus on optimized approaches like sorting or using a priority queue to handle the problem efficiently. Precision in calculations is another critical aspect to consider. For very large or very small values of position and speed, floating point arithmetic can introduce subtle inaccuracies. To mitigate this, you can use a consistent scale for your calculations or rely on integer representations whenever possible. From an interview perspective, this problem is an excellent opportunity to demonstrate your understanding of sorting and greedy techniques. Many scheduling or prioritization problems follow similar patterns, so highlighting your ability to identify and implement these strategies is essential. Additionally, be ready to explain the trade-offs between approaches. For instance, you should articulate why a sorting-based solution is more efficient than brute force, emphasizing the difference in time complexity, such as n log n, compared to n squared. Testing edge cases during an interview is also crucial, as it shows thoroughness and critical thinking. Examples include handling zero-speed monsters, cases where all positions are identical, and large datasets. Lastly, maintain clean and modular code with well-named variables and functions. This not only makes your solution more readable but also leaves a strong impression during coding interviews. This problem shares similarities with several other LeetCode problems, making it a valuable addition to your problem-solving toolkit. For instance, LeetCode 253, Meeting Rooms 2, involves prioritizing events based on their end times, which is conceptually similar to sorting monsters by their time to reach 0. LeetCode 452, minimum number of arrows to burst balloons, also relies on sorting intervals and optimizing for minimal actions, while LeetCode 56, merge intervals, focuses on interval manipulation using sorting. Another related problem is LeetCode 621, task scheduler, which emphasizes scheduling tasks efficiently to minimize idle time through greedy approaches. When considering alternative solutions, brute force is a possible starting point. While it has a worst-case complexity of n squared, it may be suitable for small inputs or as a baseline to validate more efficient methods. However, a sorting-based approach is generally preferred, as it reduces complexity to n log n. This approach is not only efficient for most input sizes but also straightforward to implement, making it a practical choice in both interviews and real-world scenarios. Another effective alternative is using a priority queue, or heap, which provides additional flexibility for dynamic processing. While the time complexity remains n log n, a heap allows you to handle real-time decisions more easily, such as dynamically determining the next monster to eliminate. This can be particularly useful in scenarios where the input data changes or when you need to make decisions incrementally. However, it's worth noting that priority queues can have higher constant factors compared to sorting-based solutions, which may make them slightly less efficient in practice for smaller datasets. Overall, understanding when to use sorting or a priority queue depends on the problem's specific requirements and constraints, and being able to explain these trade-offs effectively is a valuable skill in both interviews and real-world problem-solving. Great job! We've successfully completed problem number 1921, eliminate maximum number of monsters. Today, we reviewed the brute force approach and emphasized the importance of optimization techniques. Remember, practice makes perfect, so keep challenging yourself with similar problems. Thank you for joining me, and don't forget to like and subscribe for more tutorials. Happy coding, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!